What's up everyone? In the last video, we have seen a few examples of using the residue to find out the partial fraction decomposition. So this time, we're going to see what we can do or how we can use the residue to figure out the partial fraction decomposition in general. So let's start with our setup. Suppose we have a rational function f of x, which is written in the form p of x over q of x, where p of x and q of x are functions with any complex number coefficients. And also, let's see, what do we and also we have the degree of the polynomial p of x is strictly less than q of x, so that this rational function f of x is a proper fraction. Then suppose we somehow know the factorization of the denominator q of x in the form c times x minus xi to ki power for I from 1 to n, where the xi is representing the roots of the polynomial q of x, and c and xi are just any random complex number with the condition c is not 0, of course, and also k of I is any natural number, so that we'll make sure that the exponent is always positive. Then we can rewrite this fraction into the following form. By the idea of partial fraction decomposition, we will get the fraction is written as the sum of x to some number over x minus xi plus some number over x minus xi to the second power, all the way up to the highest power ki. That is based on what q was in q, and of course we also have I from 1 to some n to tell us how many different roots we have in the polynomial q of x. So we can just abbreviate it into this closed form here. So this is our setup. Let's see how we can actually find the a up here. And again, the a here is just the coefficients of each of the fraction. And we'll actually see how we can use the residue to find out what we should put in the coefficients. So let's jump into the for the coefficients a of ij, we can find out the number. We can find out the coefficients by the residue of the following. We'll write it as g of I. Let's see. We'll write as g of ij times, well, okay, so this is the expression that we have for finding the coefficients of each partial fraction. And we have a sub ij is equal to the residue of g sub ij comma xi, where again xi is just the roots that we have in the fraction. And a sub ij is referring to the coefficient of the xi term with some power in the fraction, where g here is also a function. G of ij, well, g sub ij of x is in fact equal to x minus x of I, or x sub I, raise it to the jth power times the original function f of x. How do we get this? Actually, there's a typo. -1 power. So where did this come from? Well, it is actually based on the uniqueness of Laurent series, or known as the complete version of Taylor series, where you sometimes see it as 1 plus, for example, a Taylor series can look like can be like 1 plus x. Well, let's use this as an example. X squared over 2x and plus this, and then all the way with an end, which is also known as taking the constant term and then add the x to the first power term and all the way up to x to the infinity term. Something like that. And then, yeah, we have the following expression. This is the Taylor series, and then the Laurent series will also include the other direction, which is the negative exponents. So we will get something of the form for n starts from negative infinity to all the way positive infinity of a sub n times x to the nth power, and that's the Laurent series expansion. And using this expression here, we see that if we want to find the residue or so using this expression here, we can actually find out the a to the negative first term, which is also the same as this following form. And in fact, we just gave this a name, the residue. So this is where the word residue come from, and also giving us the idea that how we can actually get the expression above. So if we want to generalize this relation right here, what we will get is we will get a sub ij is equal to a residue of the g function, which in fact can be written as 1 over k sub I minus j raised it to actually take the factorial of it times the limit when x is approaching to x sub I, of course. And this is where we trying to find out the residue of the k sub I minus j derivative of the product x minus x sub I raised to the k sub I power times f of x. And this is the general expression of finding the coefficients that we want in the partial fraction decomposition. So we can even double check whether it's true or not for our special case when we want to find out the coefficients for the linear term. Suppose that the highest power of some roots x of I or x of I is just 1, meaning if ki is equal to 1, we can now reduce aij, which is only be possible when I and j are both 1, will be equal to, using this, we will get 1 over 1 minus 1 factorial times the limit with 1 minus 1 and dx to 1 minus 1 power times x minus this raised to the first power times f of x. And if we simplify all of them, 1 minus 1 is 0, 0 factorial is 1, so this term is just 1, and we're taking the limit where d over dx to 1 minus 1 time, meaning that we have we don't have to take any derivatives. We have we take the zeroth derivative, meaning that this term we're not doing any extra operation here. So we just end up with the limit as x approaching to x sub I of the quantity x minus x sub I to the first power times f of x, which is the same as what we found out yesterday, what we found from the last video, when we can use the covering method.